Today we're going to take a look at the dot product. So we talked in our last section about scalar multiples. We talked about addition and subtraction, but we didn't talk about anything with multiplication. And so multiplication takes on two different forms when we're working with vectors, and the first one's the one we're going to work with today, which is called the dot product. Please help me today if I miss any of my vector hats, because they're important with what we're doing today, because I'm going to be moving between vectors and scalars like frequently, and I will probably miss some along the way. So if you see me miss something, let me know and we'll get it right, because I don't want to be wrong in your notes. All right, so first, a definition. The dot product of, and we'll write it down for 2 dimensions first, the vector u with components u1, u2, and v with components v1, v2, looks like this. So it is u dot v, and what we do is we take each of the components and we multiply them by one another. So u1 multiplies by v1, u2 multiplies by v2, and then we take their sum. And notice what we have at the end. I started out with 2 vectors. What do I have at the end of a dot product? A number, right? I have a scalar. Yeah, so when I do a dot product, I don't end up with a vector at the end. I end up with a scalar at the end. That's important. Yes, ma'am?
But is it u1 v1 plus u2 times v2?
Yeah, sorry, it's not a dumb question. It's a typo. Oh, goodness gracious. Thank you, Hannah. All right, make sure and fix that if you wrote it down wrong as I did. So sorry. It's right in my notes. We can do the same thing with 3 dimensions, and it will just 3-dimensionalize this like everything else we were doing last time, right? So we're going to have u1, u2, u3, v1, v2, v3, and multiply them component-wise and then add them together. So likewise, if u is u1, u2, u3, and v is v1, v2, v3, then the dot product of u with v is u1, v1 plus u2, v2 plus u3, v3. As expected. We're going to do some examples, but before we do, I'd like to talk about some properties of the dot product. And probably have enough space on the screen to put most of them, so we'll get started on the screen. We'll do theorem 11.4. Properties of the dot product. Okay, so for vectors, u, v, w, and scalar c, the following will hold. So the first one is that u dot v is equal to v dot u. Do you remember what that property is called when you've seen it before? Yeah, it's commutativity. And this seems reasonable because the dot product puts us back into just real numbers, right? It's a scalar. And it doesn't matter the order in which I multiply my real numbers either, right? Because the real numbers have commutativity. So we get this one based on the real number system. How about this one? So this one actually looks like a property you've seen before as well. So u dot v plus w is u dot v plus u dot w. What's that property? Mm-hmm. A distributive property. And again, all of this results in scalars, so you could actually find both of these two sides very easily with the scalar definition that we had before, or above on the screen even, and show that all the same components fall into place. The third one's going to look a little different, but it actually, again, will make sense based on the things that we've done before with real numbers too. So if I have a scalar multiple times uv, I could take the scalar multiple times u first, and then multiply that by v. I think I'll put some parentheses in. Right, so it's indicating some ordering here. Or I could do the scalar multiple times the v instead, and then do the dot product with the u. Right, scalar multiple is just multiplying by a number, so it won't matter which vector gets multiplied. The fourth one talks about the zero vector. So the zero vector is just a vector with all component forms of zero, right? So if I multiply zero, not multiply, if I do a dot product of 0 with v, what should that equal? 0. So this is an identity property. I need one more, so let's move these up just a tiny bit. All right, number 5. If I were to take the dot product of v with v, it's something you've actually seen before, but expressed a little differently. It's the magnitude of v without the square root or squared. So v dot v is the magnitude of v squared. So the first part of what we're going to do today looks like a lot of arithmetic. So if you want to grab a calculator just to be able to do things quickly, it probably will help you. We're going to do a bunch of different components of things, different types of questions, but they all relate to those properties and the definition that we've seen already. So I'm going to make a list of what we're going to compute. So this is example number 1, and we're going to compute the following. So first we're going to compute u dot v. Then we're going to do u dot u. C is the magnitude of u squared. D is u dot v. And then times the vector v, because it's going to be a scalar now, so a scalar multiple of v. And the last one is u dot 2v. I think I got them all listed. And we need some vectors to make this work, so we're going to use the vector for u as 2, -1, 3. And for v, we're going to use the vector 0, 2, -4. All right, so u dot v, I'll probably show you a little bit more work than you really need to see, but just so that we have it clear and make sure everybody's on the same page as we start. We're multiplying component-wise. So this would be 2 times 0 plus -1 times positive 2 plus 3 times -4. Does that all look good? Okay, so if I multiply all that out, what do I get? -14 is it, yes. On B, we're going to do u dot u. So again, we're multiplying it component-wise. So u with itself would be 2 squared plus -1 squared plus 3 squared, right, times itself. And if we multiply this and add them together, oddly enough, we get 14. Okay, so there's nothing special about this particular one. It just worked out that they're the same. That's not a property in general, okay? I know they're not exactly the same, but they're also not necessarily always opposites of each other like it looks like they are. C asks us to find the magnitude of u squared. But one of our properties told us that the magnitude of v, that's how we wrote it, squared was the same as what? Yeah, v times v, so this is u times u, which I've already done. Yeah? So don't recreate the wheel if you already see that it's the same thing you've already done. Just state that and move on. That one's 14. D wants us to do u dot v, which we've already done, so we're not going to redo that. We're going to use it, times v. Well, u dot v was negative 14, and then v is 0 to negative 4. So this is a scalar multiple now of the vector. We learned how to do that last time. We're going to just multiply it through. I'm going to get 0, negative 28, 56. Okay, easy enough? Okay. E. U dot 2v. Now, we could do the problem exactly like it's stated, and it wouldn't be that difficult or a big deal. We could double the vector v, and then we could do the dot product with the vector u. That would be fine. But, again, one of the properties that we just discussed says that 2 that's sort of associated, if you will, with the v right now could just be moved to the front. And that's friendlier. Why? Right, because I already know what u dot v is. If I did it the other way, I'd have far more steps. They may not take very long, and they may not be that time consuming, but I'd still have further to go. So this is just 2 times negative 14, or negative 28. So when we get to the written work, some of your problems will have multiple steps, right? They'll be like this, but that doesn't necessarily mean it's a long problem. We did that problem in, I wasn't timing us, but it was pretty fast, right? All the pieces of that problem fell together pretty nicely. All right, there is another piece that we're going to do in this section of the dot product because it uses the dot product, okay? And what we're going to look at next in Theorem 11.5 is about angles. So Theorem 11.5 says it's called the angle, or not called, it is an angle between two vectors. That's what we're going to be looking at. Two non-zero vectors. And it says the following. If theta is the angle between two non-zero vectors u and v, where theta is between 0 and pi, then the cosine of theta equals u dot v over the magnitude of u times the magnitude of v. In particular, we're not going to be given theta. We're going to be given the vectors, and we're going to find the theta, okay? But again, also in general, this isn't unit circle kind of questions. Your calculator is going to be very useful and in fact necessary because these, is this something you...
The mathematical basis is like u dot v is cosine theta v in magnitude of the two. I'm like, where does that come from?
Yeah, and sometimes you'll see this written as well with the u magnitude, the magnitude u magnitude v written over on the other side with the cosine of theta. This is how your book presents it, so I'm going to present it like this, but they're equivalent, of course.
So, could you also say it's multiplying the unit vectors for u and v?
In some sense, yes, but you're doing a dot product on top,
Yes.
not just multiplying, so we have to be careful with our language a little bit, but yeah, you have that idea, because you are taking the unit part to it by the magnitude pieces on bottom, yeah. Okay, let's see how it works. We could actually do that for this particular problem, because we've already found the u dot v. We didn't find u, the magnitude of u. We did find the magnitude of, we found the magnitude of u squared, so we would have that one pretty easily. We didn't find the magnitude of v, but it wouldn't take but a couple more steps to be able to do it for this particular problem. Let's take a look at another one. We'll change the vectors up a little bit. All right, so we're going to find the angle between u, which is I plus 3j minus 2k, and v, which is 2I minus 3k. And we're going to do this in radians, and then we'll convert it also to do it in degrees. Okay, so, when I'm doing things in calculus, in algebra, I usually just kind of like do it all at one time, but this has 3 separate pieces, and it seems reasonable to just find the 3 separate pieces and then merge them together. So that's how I'm going to approach this. We need to find u dot v. That's one of the things we're going to find. We're going to find the magnitude of u, and we're going to find the magnitude of v. And you could do that in whichever order you'd like. We'll do it with the magnitude of uv, u dot v, since it, sorry, not magnitude, with u dot v first, since it's on the numerator. So if I were to do this with u dot v, I'd have 1 times 2 plus 3 times, it's actually 0 because there is no j component in v, and then negative 2 times negative 3. And what will that give us? It'll be 8. Good. Magnitude of u, so that's got the square root, and then it's got the components squared. So I have 1 squared plus 3 squared plus negative 2 squared. So what will that give me underneath my square root? And then we'll do the same thing for v. So v is 2 squared plus technically 0 squared and then negative 3 squared. Square root of 13. So using all of that, I can put it into the format that I saw earlier. So the cosine of theta is the u dot v, so that's 8, over the square root of u, which is, or I'm sorry, over the magnitude of u, which is square root 14, and the magnitude of v, which is square root 13. You can get a decimal approximation if you want to for what's ever on the right-hand side. We're going to let our calculator do all of it for us in a moment anyway. If you wanted to merge the two values together on bottom, you could do that. Right, the 14 and the 13, merge them underneath the radical. I'll show you that too in a second. But whatever we have on the right-hand side, we're trying to find theta. And how do we find theta when this is definitely not a unit circle kind of value? Arc cosine or inverse cosine, right. Exactly. So we're going to take the inverse cosine, or arc cosine if you prefer, of 8 over, and if I do multiply the two on bottom together, it's the square root of 182. So there's several things you could do in your calculator. Most of your calculators allow you to just enter it straight like it is. If you want to do 8 over the square root of 182 first and then do the arc cosine, you could do that. It doesn't make any difference. Do make sure that you're using the entire decimal expansion if you decide to do it in steps so that you get things as accurate as possible. And your book tends to tell you, WebAssign will tend to tell you how many decimals to use at any given point. We're going to use 3 by default right now, but obviously if it tells you to use something different, just go with what the directions say. So I got for theta in radians 0.936. Is that what you guys have? Okay, so you could obviously just change it back into degrees in your calculator, as in like tell your calculator to change the mode. I think that's kind of dangerous because I don't really want you to accidentally keep your degrees mode showing up on your calculator. So I would simply, to turn it into degrees, take the 0.936 and just multiply by 180 over pi. And then you can, and your calculator will still be doing that for you. But then you don't run the risk of accidentally not putting it back into the radians later, because we definitely want to keep things in radians. The other thing I would do is I would not use 0.936. I'd use the expansion in your calculator, because it's more accurate. Even if we rounded the 0.936, we don't really want to use the rounded 0.936 to find the degrees. So if I leave it as accurate as I can, I'm going to, I get anyway, 53 point, looks like 630 degrees if I use 3 decimals. Is that all right? Okay, so dot products tell us one very interesting fact that we haven't discussed yet. Dot products actually tell us when vectors are orthogonal. So do you remember what orthogonal means? Have you heard it before? No? Okay, so orthogonal is what we call perpendicular in 3 dimensions. Okay? So this is just perpendicular, but in a 3-dimensional sense instead of in a 2-dimensional sense. So it has the same feel to it, though. So the vectors u and v are orthogonal. And feel free to jot yourself a note that that means perpendicular in 3 dimensions. When u dot v is 0. So everything I've done so far has not been orthogonal, because I have not gotten yet any dot product of 0, right? So we should probably see one that is, because, you know, they do occur. So we're going to determine, this is example 3. If u and v are orthogonal, which we just talked about how we're going to do that. If they aren't orthogonal, another option would be parallel. All right, think about lines, right? Parallel lines, perpendicular lines. That's what we're looking at here. And then the third option would have to be neither, which is what we've seen today, actually, so far. The examples are neither. And our vectors are, we're going to just use some, we're going to use a couple with two components. It works the same with 3 components. This section, you're going to see them bouncing back and forth the whole time between 2 components and 3 components. We did one section that was all 2 components, 11.1, all 3 components in section 2. Now we're going to be doing both. So we're going to test to see if they're orthogonal. Before we test to see if they're orthogonal, how can we know for sure that they're not parallel?
Is there a scalar multiple?
Right. So they're not scalar multiples of each other, right? So it's definitely not parallel. So if orthogonal fails here, it's going to mean the answer is neither. So we can see that one at a glance. So let's do u dot v. So I have 2 times 2 plus negative 1 times 4. And what do you see happening? 0. So these vectors are orthogonal. Okay, the next thing we're going to talk about is something called projections. So I want to draw a picture first, and then I'll write the definition all out formally for this. But we're just going to draw a vector. Say like that, okay? The way we've defined our vectors all the way along is in component form, right? There's how far, sort of ij component forms, ijk component forms. And we're thinking them in terms of like an xy or an xyz axis, right? And so the terminal point being at the origin and the initial point being at the origin, and then the terminal point being somewhere that identifies the x, y, and z, or the I, j, and k components. So if we were to take this image and we were to project it down onto the number line, whatever the x value here, don't write this down just yet, just pause for me. Whatever the x value is at this point is what we would be right here, right? And this piece right here would be the length in the sort of x direction. Well, what we want to do is we want to do that not down on the x-axis, but on any other random vector. Okay, so we're going to take one vector and project it onto another one. So it's going to look something like this. So I'm going to take this, and I've got another vector, but it's not necessarily the x-axis, y-axis. It's just another vector. And you want to imagine projecting it down onto that component, or that new vector. My lower one's a kind of a bluish color. So if you were going to sort of like shine things down, like almost imagine like rays of sunshine coming down like this, and you were to do this, they would cast a shadow below, right? So the shadow that would be cast would be down here. Oh, that's not good at all. Would be down here, and we would take this, and it would actually form a right angle, and this would be the component along that vector of it being projected down. We're always projecting down at a right angle. Okay, so it's not like the sun when the sun projects, because the sun is not always coming at a right angle. Sometimes you're like this because the sun's going, your shadows get longer at certain points of the day, right? So that's not what we're talking about. We're projecting down at a right angle. So what happens is this component that it projects down onto, let me draw it with another arrow. When it projects down onto this, and it's like about right here, let's say, this component is what we're going to call the W, well, this vector is U, and this vector is, how are they defining it? V. So we're projecting U down onto V, and we're going to call this red one that I marked the W1 component on V. So this is projecting onto V. We can also project onto the complement of V. And so it looks like this. So kind of think about like your x and y axis. They're perpendicular to one another, right? If I were to form a perpendicular line or a perpendicular vector to the one that I have, I'm trying to draw it well. That looks believable, I think. And if I were to project over to this side, and I were to form that right angle, I need a dotted line. I can't keep mine straight, turning my screen this much. That's reasonable. I think we're okay with that, right? All good? That looks like a right angle. This looks like a right angle. Okay. So this projection over here that I created. Oh, good grief. That's the one I want. That projection over here is called W2. So it's almost like, this is my W2 vector. It's almost like I'm taking the axes, right, and I'm sort of tilting it somehow, right? That's the image you should have, is that you've tilted the axes. Normally it's straight up and down, like in our image, and we're now putting it at an angle, okay? So let me write out the formal definition for what's being drawn here next. So each of these W1, W2s have names. So we're going to let U and V be non-zero vectors. Moreover, we're going to let U equal W1 plus W2, where W1 is parallel to V and W2 is orthogonal to V. Okay, that's the image that I have on my screen above, that picture. I've got parallel vectors, W1 and V1, and V, rather. Okay, parallel means that they're the same, not the same length, they can be different lengths, but they're in the same direction at the same angle, going the same way, right? And then we have the orthogonal to that, namely the W2. Then there's some names for these. So the first one is this. W1 is called the projection of U onto V. Or the vector component of U along V. I'm most likely to call it the projection of U. And it is denoted by W1 equals the projection of U along V. So V looks like a subscript in this notation. It also has the vector head on top of it. It's just that I'm getting things so tiny at this point, it's hard to draw them in. That's not too bad. Okay. But if I define W1, I need to define W2 in a similar fashion. So W2 can actually be defined using W1. W2 is actually the vector U minus the vector W1. And this is the vector component of U orthogonal to V. So how do we find projections? Well, it's going to look very familiar. The pieces are all things we've done. So this is theorem 11.6. Projection using, what's this lesson name? The dot product. Okay, so if U and V are non-zero vectors, then the projection of U onto V is, okay, so the notation, I keep going to spell my projection wrong. Project notation says projection of U along V, like that. And it's equal to the dot product of U times V, or U dot V, divided by the magnitude of V squared. And this will be a scalar that gets multiplied by the vector V. I'm really trying my best not to put dots for multiplication right now because we're using dots in a very unique way. Normally I put dots for multiplication all the time. Okay, ready to try one? Definitely. That's what I heard you say. Okay, so example 4. We're going to A, find the projection of U onto V And then B, we're going to find the component of U orthogonal to V. Okay, so I don't have it on this, oh, I do have it on the screen. It's not my paper that I'm looking at now. The projection of U onto V means I have the dot product of U and V, and it means I also need the magnitude of V. So those are the two things I'm going to find. I need to find U dot V, and I need to find the magnitude of V squared. Or you could say equivalently that this one is simply V dot V, right? All right, so U dot V. So we're going to multiply these component form. Oh, did I not give them to you yet? I'm so sorry. Let me move this down and put it in between there so I can see it above too. All right, U is 2, -1, 3. I think I've used that multiple times now. And V is 1, 2, 2. So multiplying component-wise, I have 2 times 1, once again, dots. 2 times 1 plus -1 times 2 plus 3 times 2. What does that give us? 6, yep. Now we're going to do this with V, so we're going to square each component. So I have 1 squared plus 2 squared plus 2 squared, which gives me 9. Okay, and I'm ready to do the projection. So the projection of U along V would end up being the 6 for the dot product over the 9 for the magnitude squared. And I'd be multiplying it now by the vector V, which is 1, 2, 2. 6 over 9 is actually the same as 2/3. So we're really going to be distributing a 2/3 through the vector 1, 2, 2. So 2/3 times 1 is 2/3. What do I get for the next one? And 4/3. So this is the projection of U along V. We also called it W1 if you prefer. In fact, I'm going to call it that here for the next part to show you some things. This is W1. And then the next piece is to find that component that's orthogonal. So to do that part, we're going to find W2, which is the vector we're working with, which is U, minus the W1 vector we just found. So U was 2, -1, 3. And I want to subtract off the 2/3, 4/3, 4/3 that I just found. So we're going to subtract them component-wise, just like we did in 11.2 and 11.1. So what is 2 minus 2/3? That one's 4/3. How about -1 minus 2/3? Or sorry, 4/3. -1 minus 4/3. -7/3. And the last one is 3 minus 4/3. 5/3. Okay, any questions on that? All right, let me get you the homework. It's not near as long as last time. But remember, there's going to be some of them that have those multiple parts to it, so don't be surprised when that sneaks up on you. So this is page 777. And our problem numbers are 5, 10, 12, 15, 23, 24, 39, and 42. And a bit of warning, I still have not, well, let me just stop this video first.